in a simple linear regression? Well, we have a value y, as we know, and we've got a column essentially for our beta naught and our beta 1 and our x's. And so we can write an equation for every observation, right? So this particular observation, y1, we're saying is equal to our intercept, which is a constant, right? Plus our slope, which is, a constant that we've calculated, times whatever the value, the concurrent value of x1 is, plus whatever's left over, right? This is the error. Yeah. And then y2, similarly, is equal to the same thing, but it depends on, so the value of y depends on the value of x, right? According to this function. And this is the bit that we're missing. Right, so we can write an equation for every observation. Right? In matrix form, it looks like this. Right? This is my vector of my y values. This is basically my equation that I'm going to do. And the bit that's left over is the bit I haven't modeled. So actually, this is the bit that's the model, and this is what's left over. Okay? So if you think about this, right, what is that? Well, we're saying y1 is equal to, well, it's equal to beta naught plus beta 1 times x1. Well, if we take this and multiply these across, it's equal to beta naught plus beta 1 times x1. Right? y2 is equal to, take this row, we duck dive it across, beta naught plus beta 1 times x2. Right? And what's left over is the equivalent row. Right? So that's, you can see it in matrix form. It's very simple because essentially it comes down to this. Right? Our y vector is equal to a matrix that is composed of a column of ones and then our x variables times, and this is the bit we need to solve for, the betas. Right? This is the one thing we have to calculate for. Times whatever vector this is, right? And that's the bit that's left over, plus what's remaining. Right? So this x is commonly known as the design matrix. Right? Beta, I should say, is the parameter vector, right? The vector that contains all your estimates of your parameters. Right? We've got our error vector, and we have our response vector. And because this is a univariate technique, it is just a vector. It's not a matrix at this point in time. Okay. So we want to work out what beta is. So just in case I went a bit too fast for you, I'm going to give you a very brief refresher on matrix addition and subtraction, what the trace of a matrix is, what the transpose of a matrix is, how to multiply some matrices together, which is what we did, how do we square a matrix, and importantly, calculating what the determinant of a matrix, of a simple matrix is, what it means, I guess, and also what the inverse of a matrix is. And that's pretty important, what the inverse of a matrix is and what that does. Okay, so let me just give you a few definitions that many of you will know. A constant, I will also call a scalar, right? We'll denote those by lowercase italics, right? So a constant or a scalar is simply a single value, a constant or an observation. A vector refers to a single row or a single column of values, right, in matrix algebra. So this is a column vector here, a single column. This is a row vector, okay? Usually when I'm talking about vectors, I'll be talking about column vectors, okay? If, on the other hand, I want to talk about a vector as a row of numbers, I'll actually talk about it as x transpose, or x prime. Right? So this would be called x, so this would be called x transpose. Right, so I've already defined what a matrix is to you guys. A 2 by 3 matrix, well, what does that mean? What does the 2 refer to? The 2 refers to the number of rows. The 3 refers to the number of columns. Right, so 2 by 3 matrix is a matrix with 2 rows and 3 columns, 1, 2, 3. Right? The 3 by 2 matrix, right, so this is the transpose of x, is going to be a matrix with what? 3 rows and 2 columns, right? 3 by 3, 3 by 2. So don't worry, this won't come just like that, but just remember rows, then columns, when you're looking at n by p. Okay? So if you have equal sized matrices, then things are very simple. If you just want to add or subtract things, you simply add or subtract the individual elements in them. Okay, so if I've got this matrix A and this matrix B, and I want to calculate A plus B, well, the top left values, I just sum that, sum that, sum that, and sum that, right? So it's just me simply adding all the elements within the matrix, right? Because they match up, there's a one-to-one correspondence. So it's very easy to do. Likewise with subtraction, which is just another way of adding, of course, right? Just adding a negative number. So it's the same thing. Right. So if I was to ask you very quickly, calculate A plus B here, go ahead and do it. It should take you all of 9 seconds to do. All right, what's the answer? Let's read across the rows.
7, 6, 8,
15, 15.
Okay, you guys get the idea, right? It's not hard, right? 7, 10, 8, right? In the bottom row. Okay, like I said, I just want to make sure everybody has the basic groundings for this. So a square matrix, not surprisingly, is what happens when you have n equal to p, right? In other words, you have the same number of rows as you do columns, or vice versa, right? So the covariance matrix is a square matrix, right? Remember we have a diagonal, all the variables, number of variables down the diagonal. And not only that, the covariance matrix is a symmetric matrix. And what do I mean by a symmetric matrix? I mean the values above the diagonal. So this is the diagonal here, down there, right? These are the diagonal values. It's symmetric if the values on either side of them are mirror images of one another, right? Does that make sense? Right? So if this was a covariance matrix, right, we'd say, hey, this is the variance of variable 1, the variance of variable 2, the variance of variable 3. This is the covariance of variable 1 and 2, variable 1 and 3, and 2 and 3. Right? And it doesn't matter if I look at the top half or the bottom half, I get the same answer. Right? Does that make sense? Yeah? Right, so the transpose, which I've already referred to, right, simply is when I switch the rows and the columns around. All right, so here I've got a 2 by 3 matrix, right? I transpose it and I end up with a 3 by 2 matrix. Right? So if you transpose a matrix, you can make it possible to multiply them together. And in fact, often it's very useful to have something called X transpose X. So I will often denote the transpose with a little prime here, little dash. Sometimes you'll see it as a little t. XT, meaning X transpose X, right? So this is the value of that matrix times that. X transpose times the X matrix. And in that case, you can multiply them together. And I haven't talked about multiplication, but we will very shortly. Right, the trace of a matrix is pretty useful in multivariate statistics. It is simply the sum of the diagonal elements, right? So the trace of this matrix, well, what are the diagonal elements? 2, 1, 3, right? So the trace is 6. Does that make sense? It's not hard. It's just some jargon terms. So the trace of this matrix is 7, right? Right, the inner product and the outer product is, here we go, x prime y. What's that going to be? Well, what's x transpose? 103. And what's y? 246. So then it is going to be a scalar, right? You multiply these two things down. And I haven't actually talked, I probably should change the order of the slides. When you multiply your vectors together, right? Remember you duck die them, so it's going to be 1 lot of 2, 0 lots of 4, 3 lots of 6. And you sum them all together. But the main thing is if you have an inner product, a transpose of a vector times the column vector, you end up with a scalar, right? You're going that times that, basically you end up with a single number. If you go the other way, that times that, you have a different answer. Right? That's your outer product. The outer product is x times transpose y. So the first one was x transpose times y, right? This is going the other way around. This, what we've done is we've transposed this instead. And what's that going to be? That's going to be a matrix. Right? This is saying we've got one lot of the row 246, and then 0 lots of the row 246, and then 3 lots of the row 246. Right? And that's your answer. 246, then row of zeros, and then basically a row that is 3 lots of this. Right? That's called the outer product. Right? This is probably only important if you're going to be doing a lot of matrix algebra stuff. Most of the time it's not going to be particularly important at this point in time for you guys. So, but you do need to know how to multiply two matrices together. So the duck diving method is what most people have learned at school, right? Back when I did my school work, but we hadn't invented calculators back then, right? So I had to go through and carve my own pencil from a tree because we didn't have lead, and calculate by hand. Kidding. Tough audience, huh? I like this whenever there's a joke from now on, huh? Okay, so what's the duck diving method? Well, you take your row and you dive it down like a duck. Think of it like a duck is going along. It swims in a. When a duck, it sticks its ass in the air in the water, right? It dives down. That's what you're doing with the row. The row is the duck, and then it dives down, right? And then you multiply all of those elements together. So this row 1 and 2, right, comes down and dives down. This is the 1 at the top and the 2's at the bottom. Right, so you got 1 times 1 plus 2 times 5, right? That's what's going to go there. And then you're going to do the same thing across here for this element, and the same thing across there for that element, right? And that's going to give you this row at the top, and then do the same thing on the second row, the 3 lots of 1 plus 4 lots of 5, 3 lots of 3 and 0 lots of 4. You can fill your matrix up, right? So this is important that you understand, conceptually, right? So this is why I asked you to make sure you knew how to do this, because I'm going very quickly through it. Right? But A times B is not necessarily the same thing as B times A. Turns out. In fact, you can't do it. You have to have the same number of columns as you do with the rows, essentially, to be able to multiply two matrices together. Same number of columns in the first matrix as rows in the second. Okay, so let me give you another example. Well, this is a more complicated example. This is more for your just your notes, so that you can understand, right? So I don't really expect you to go through this, but what would you do here? We've got n is the number of rows in matrix A, B is the number of columns in matrix B. So here is matrix A, here is matrix B, here, right? So P is the number of columns. As long as the number of rows is equal to, the number of columns in B is equal to the number of rows in A, then we can calculate our matrix, right? So this is a 3 by 2 matrix, and this is a 2 by 4, right? When you're multiplying them together, the 3 times 2, 2 times 4, as long as those two things match the 2 and the 2, then you can do a matrix multiplication. So what do you calculate here? Well, it's the same, right? It's just more practice. Duck dive it down. 5 times negative 5 plus 3 times negative 2. That's that element. Bam, 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 so on and so forth. So you're going to end up with a very big matrix, right? But you understand the basic idea of it, right? Hopefully. Okay. And when you can do it and when you can't do it is the main thing, right? So this line here is when you can do it. Okay. So what are you doing with matrix multiplication? What are we doing? That's the important question. Fine, we know the mechanics of it. The mathematicians know you can do very complex stuff. So what is it that you're doing? So this is a pretty useful way of looking at matrices to me, is just to think of it as a function that's going to act on a vector of some sort. Right? What do I mean by that? Well, here's a vector, right? Column vector, 1, 1. Right? So I can draw this as a line going, well, it's got a 1 in this direction and 1 in that direction, so my resultant vector is in this way, right? 1, 1. Right? So this is my vector x, and that's equal to 1, 1. Right? If I multiply that vector by a matrix, what's going to happen? say I multiply it by this vector, the vector x by a. What happens? Let's say a is, I don't know, 3. So k was 3. What happens? So you transform what? Transform the vector is what you're doing, right? What happens is you end up like, this is a times x here, and it's actually skewing it. It's pulling it across now. Because if you multiply that out, you end up with a vector that is k, the first row is k, and then you've got a 1 at the end. Right? So it's a function, it's basically change your vector. You got your vector. If you get your matrix to act on that vector, you end up with something else. So you can think of it as a function that is acting on a vector. So in goes your vector x, right? And out comes a vector a times x. And what is a doing? It's linearly transforming your vector x that you're multiplying it by. Right? You're doing a linear transformation of the vector that you're multiplying it by. Think of the vector, this one here, 0, 1, 1, 0. What is that doing to it? It's called a permutation matrix. Let's say we've got a vector, I don't know, 2, 4. Right? So if we multiply a times x, what do you get? What's the top row going to be? 0, 1. Right, so this is, what is this? 0, 1, 1, 0 times 2, 4, right? So that's equal to what on the top? 4, and the bottom end? 2, right? Well, I've just swapped things around, haven't I, essentially? That's why it's sort of permuted the values with one another. Right? So you can think of it, hey, there was, once again, we've got this vector, and I've done something funky to it with this matrix, and I've transformed it in some way. The result I've got is a linear combination of what I had initially. Right. How about a vector like this? 1, 1, 0, 0, 2 ones across the diagonal, and lots of zeros elsewhere. What is that going to do? Any ideas?
Shield a certain number in the vector.
Right. It kills a certain number in the vector. That's a very graphic way of putting it. I know what you mean, but can we describe it a little bit more accurately? So our vector now could be, it has to be 3 long, right? 1, 3, 6, 7. Right? It just becomes what?
One less dimension.
What's that going to be? This is x. And that's a. Right? Everything goes down to 0, right? One lot of the first, one lot of the second, and nothing of the third. Right? So basically what happens is you end up with a vector that was in 3 dimensions, right? And it loses everything in that, whatever vector you got in there, then gets basically projected down into 2 dimensions, essentially. So it's a projection down from your 3-dimensional space into your 2-dimensional space, where that last dimension is the third one. The 6 gets lost. Okay, how about this vector here? Let's say we've got A is 1, 1, negative 2, 4, right? Now I can choose any value of x and y, right? And then I multiply it. So I'm going to denote the values of x, y in red in a graphic. And then the resultant matrix is going to be in blue here. So for any particular value that lies on this unit circle, so this is just a vector of some kind, right? It could be 1, 1, it could be 0, so this is going to be 0, 1, 1, 0, this could be, I don't know, square root of 2, square root of 2, or something like that. This is all a certain distance. What happens is it comes out with the same sort of transformed value, doesn't it? right? So these are the possible input vectors. These are the possible output vectors. Pretty much every possible vector in 2D space you've got. So you can see this idea that here's your vectors. This matrix is transforming it in some manner, right? That's the basic idea. It's a function that acts on vectors. What that function does, well, we'll find out, right? In some ways. This is a little note. It's by Brian McCullough, who was my old PhD supervisor, showing how the order of operations matters. Right? This is saying that A times B is not the same thing as B times A. And that's because you can think of this thing as your matrices are functions that do something to the vector, right? So here we go. Let's say that the matrix A is a reflection, and then B is a rotation, right? So B is a rotation 90 degrees. When you multiply something by B, a vector by B, it will come up with a resultant vector that has been rotated by 90 degrees. So let's start with a vector here. If we multiply it by A, well, we know that whatever matrix A is, this is it here, that's a reflection in the x-axis. So you end up with down here, right? And then B, if we multiply that by B, you end up with this value here, right? Because it's rotated 90 degrees. Right? Let's say we change the order of things, right? So instead of doing BAX, we did ABX, right? So the first thing is we multiply it by by B, that's the rotation, 290 degrees, and then we multiply that by A, which is a reflection. You end up with a different answer, right? So this just shows you that the order of the operations actually matters with multiplication for matrices, right? Not so much for when we're dealing with regular numbers, right? But for matrices, things do matter. The order matters. Okay, so let's talk you through the most common matrices that you're going to deal with. First one you probably are all familiar with is the identity matrix, or technically it's the multiplicative identity matrix. And why is that? Why is this matrix called the identity matrix?
It gives the identity.
Sorry?
It gives the identity of the matrix.
What does that mean?
It's neutral, not changing the values of the matrix.
That's right. If you multiply any vector by the identity matrix, you end up with the same thing. It doesn't do anything. Right? It's like multiplying things by 1. It hasn't changed whatever you put in, right? So, if we multiply a matrix by the identity matrix, you end up with exactly the same input matrix, and same thing with a vector. Right? So that's the multiplicative identity. What would be the additive identity? So what matrix would you have to have if you're adding to it that wouldn't change the input matrix? Just a bunch of zeros, right? Yeah, because whatever matrix you had, add a bunch of zeros to it, you end up with the same thing. So that's the multiplicative identity matrix. Right? The additive identity matrix is zeros, full of zeros. So I've already talked you through the variance-covariance matrix, right? So I don't have to go into this too much. The correlation matrix is basically your same thing as your covariance matrix, but you've standardized by the variances. Now, so covariance is correlation is always a value between -1 and 1, right? And what that is essentially is your covariance divided by your variances. So when you divide by the variances, all of these variances just become 1, right? And what you're left over with are correlations, right? So negative values and positive values. A value of +1 means a perfect increasing relationship between x and y. -1, perfect decreasing relationship. Right? So whereas these values, the covariances are difficult to interpret, these values are nice and easy to interpret. Right? Often, with the data that you get, you're going to create a model that is essentially a correlation matrix. And you're going to use this as your input. Right? And I'll tell you why. Okay, so we've talked through the covariance matrix. I don't need to go through this again, I hope. Okay, so I've stated that a matrix is a function that acts on vectors. More specifically, it's a matrix. A matrix acts as a linear transformation on a vector. Right? So let's consider what we do when we multiply a matrix by a vector. Right? If we have a matrix, if we have a vector here, 1, 2, 5, and I'm multiplying it by this vector, this matrix A, right? What do we get? Well, what we have essentially is a linear combination. The columns of AB are combinations of the column of A, right? What is it in fact? Well, it's 1 of the first column, 2 of the second column, and 5 of the third column, right? This is the linear combination. I'm just combining the columns of A according to this. 1 of the first column, 2 of the second column, 5 of the third column. If I add all those up, I end up with this. Right? You see what I mean by it's a linear combination of the columns when I multiply a vector by that matrix? So let's be explicit. Oops. Okay. Right, so what are we saying? So we've got this so let's multiply these again. A times B, we're multiplying 2 matrices together now. So what have we got? We're saying we have, according to this, A times B is we have 1 lot of the first column of A plus 5 lots of the second column of A. Right, that's going to be here. This is going to be 3 lots of the first column plus 0 lots of the second column. And that's going to be this bit here. And then 4 lots of the first column, 2 lots of the second column. And that's going to give you that answer here. Once again, we're combining these things, right? Combining the elements of A in a linear fashion with the elements of B. Okay, we can do that. We could also do that with respect to rows if we wanted to. It gives it the same answer. We could consider it identically with respect to being linear combinations of rows. So up to now, I was just talking about the columns, but I could talk about the rows of A and B as well if I wanted to. Right, so this is saying, what do we got? We look at A is 1, 2, right? We're saying, well, AB is 1 of the top row of B plus 2 of the bottom row of B. And the second lot of A times B is going to be 3 of the top row of B plus 4 of the bottom row of B. And that is, algebraically, you end up with the same answer, right? So whether or not you consider these linear combinations of the rows or linear combinations of the columns, it doesn't really matter. This is the key point. The columns of A times B are linear combinations of the columns of A, or vice versa. And this is important because it's going to be important when we try and work out whether or not a matrix is invertible. Right? So before we go to matrix inversion, we'll talk about squaring very quickly. So a matrix can be squared, right? Just as you know, any real number can be squared multiplying it by itself, right? To square a matrix, what do? Well, it's only going to work if we can multiply it together some way, right? So if we have a rectangular matrix, we're not going to be able to multiply that together. So we have to transpose it. So first off, you calculate its transpose, X transpose there, right? And then you multiply the transpose matrix with the original matrix. Right? So for a matrix X, the analog to X squared is X transpose X. Right? So what's the square of this matrix here? Oh, what's X transpose? There are 2 things we could do. One is going to be the sum of cross products. I won't go into the details of this. We could do X transpose X like this, or we could do X transpose. We end up with 2 different answers, in fact. Both are going to be square matrices. Okay, so do we want to do practical 2 now, or do I want to do determinants? Let's take a break. So that was a very quick summary of